Hi, I'm a tutor in Uplatz. Today we are going to discuss about Fourier theory. A sine wave is shown in figure. It is pi into sine 2 pi 40, amplitude 5, frequency 4 hertz, x-axis is seconds, and y-axis is amplitude. A sine wave signal, pi into sine 2 pi 40, amplitude 5, frequency 4 hertz, sampling rate 256 samples per second, sampling duration 1 second, and under of the signal sine 2 pi 80, signal ratio 8.5 hertz. Nyquist frequency. The Nyquist frequency is equal to 1/2 of the sampling frequency. Nyquist frequency is the highest frequency that can be measured in a signal. Periodic functions and signals may be expanded into a series of sine and cosine functions. A transform takes one function or signal and turns it into another function or signal. Continuous Fourier transform, close airways if you do like integrals. H of f is equal to minus infinity to the h of t into 2 pi DTFT dt. H of t is equal to minus infinity to infinity h of f e minus 2 pi I f t df. A transform takes one's function h of n is equal to sigma k is equal to 0 to n minus 1 h of k e power 2 pi I k n by n, or h k is equal to 1 by n, sigma n is equal to 0 to n minus 1 h of n e power minus 2 pi I k n by n. Fast Fourier Transform. Fast Fourier Transform is a very efficient algorithm for performing a discrete Fourier transform. FFT principle first used by Gauss in 19th century. FFT algorithm published by Cooley and Tukey in 1965. In 1969, the 2048-point analysis of a seismic test took 13.5 hours. Using the FFT, the same task on the same machine took 2.4 seconds. Famous Fourier transform, sine wave and delta function is shown here. Gaussian and Gaussian function is shown here. Sinc function and square wave function are shown here. Sinc function, square wave function is shown here. Exponential and Lorentzian function is shown here. FFT of FID. FT is equal to sine 2 pi FT into exponential of minus 2 by T2. F is equal to 8 hertz, S is equal to 6 hertz, T2 is equal to 0.5 hertz, and it is shown here. So for T2 is equal to 0.1 hertz, seconds it is shown here, blown up figure, and 2 seconds is shown here. Effect of changing the sampling rate is shown here. Another effect is shown here with 128 hertz and 256 hertz. Lowering the sampling rate reduces the Nyquist frequency, which reduces the maximum measurable frequency. It does not affect the frequency resolution. FHSS sampling duration is shown here. With ST is equal to green one, ST is equal to 2 seconds, and ST is equal to 1 second. Reducing the sampling duration lowers the frequency resolution, does not affect the range of frequency you can measure. Here it is shown, the graphs are shown here. For sampling time, 2 seconds and 1 second are shown here. For F is equal to 80 hertz, F1 is equal to 80 hertz, F2 is equal to 90 hertz, F3 is equal to 100 hertz, T2 1 is equal to 1 second, T2 2 is equal to 0.5 seconds, T2 3 is equal to 0.25 seconds are shown here. Measuring of multiple frequencies are possible. Here is another example also. The sampling rate is equal to 256 hertz. Polynomials, P of x is equal to 5 plus 2x, 8x squared, 3x plus 4x. For in general, P of x is equal to I is 0 to n minus 1 a x a, or P of x is a0 and a1x plus a2x squared plus a n minus 1 into x n minus 1. Polynomial evaluation honors given a coefficient a0 to a n minus 1, defining polynomial P of x I is 0 to a n minus 1 a I x I. given x, we can evaluate p of x in order of n time using the equation p a naught x into a1 plus x into a2 plus x into an minus 2 plus x an minus 1, so on. Eval ax, where a is equal to a naught to an minus 1. If n is equal to 1, then return a naught. Else, let a dash is equal to a1, a2, an minus 1. Return a naught is equal to x into eval a dash, a transpose x. Assume this can be done in constant time. Given the coefficients a naught to a n minus 1, b naught to b n 1, define the two polynomials p and q and number x, compute p of x, q of x. Honors rule does not help since p of x and q of x will I is 0 to n minus 1 ci xi, where ci is equal to j is equal to 0 to n I of j into bi minus j. A stated error will take out of n squared. The magical FFT will do it in order of n log n time. Polynomial interpolation, polynomial multiplication. Given a set of n points in the plane with distinct x coordinates, there is exactly one n minus 1 degree polynomial going through all these points. Alternate approach to computing p of x, q, x is calculate p on 2n x values and calculate q on the same 2n values. Find 2n minus 1 polynomial and thus through the points x, p naught, p x naught, q x naught, p x1, x1, px1, px1, x2, n minus 1, px 2n minus 1, px2. Unfortunately, a straightforward evaluation would still take out of n squared time, as we would need to apply an out of n time ordinal rule evaluation to 2n different points. And the magical FFT will do it in order of n log n time by picking 2n points that are easy to evaluate. A number omega is primitive nth root of unity for n greater than 1. If omega power n is 1, the numbers 1 omega are all distinct. Such 1, 1 star is shown here. 2, 6, 7, 8, 10 roots of unity in 0, 1. 2 square is equal to 4, 6 square is equal to 3, so on. Example, the complex e power 2i by n is primitive nth root of unity where I is equal to square root of minus 1. Properties of primitive square root of unity. Inverse property, omega is primitive square root of unity, then omega minus 1 is equal to omega n minus 1, and omega into omega n minus 1 is equal to omega n is equal to 1. Cancellation property. For non-zero k greater than minus 1 and less than n, sigma j is equal to 0 to n minus 1 of omega kj is equal to 0. Proof sigma j is equal to 0 to k omega kj n minus 1 is equal to omega k power n minus 1 by omega k minus 1, omega k power n omega power n power k minus 1 by omega k minus 1 is 1 power k minus 1 by k minus 1 is 1 minus 1 by omega k minus 1 is equal to 0. If W is primitive 2nth root of unity, then omega square is primitive nth root of unity. Proof if 1 omega n squared are distinct root and omega square are n minus 1, so are 1 omega square, so on. If n is even, then omega n by 2 is equal to minus 1. By cancellation property for k is equal to n by 2, we get the corollary omega k power plus n by 2 is equal to omega minus omega power k. Discrete Fourier transform given coefficients a naught to a n minus 1 for n minus 1 degree polynomial. The discrete Fourier transform is to evaluate the p values at omega 1 omega square omega n minus 1. We produce y naught to y n minus 1 where y is equal to p omega power j, that is y j is equal to sigma t is equal to 0 to I is equal to 0 to n minus 1 ai omega ij. Matrix form y is equal to fa where f I of j is equal to omega ij. The inverse discrete Fourier transform recovers the coefficients of n minus 1 degree polynomial given its value at 1 omega square omega n minus 1 matrix a f inverse y where f inverse is of ij is equal to omega minus ij by n. Correctness of inverse DFT. The inverse DFT and inverse DFT really are inverse operations, that A is equal to F minus F. We want to show that A is equal to I, where Aij is equal to 1 by n, k is equal to 0 to n minus 1 omega minus kib into omega kj. If I is equal to 0, then I is equal to 1 by n, k is equal to 0 to n minus 1 omega minus k into omega ki is equal to 1 by n, k is equal to 0 to n minus 1 of omega 0 is equal to 1 by n is equal to 1. If A and G are different, then it will be equal to 0 by cancellation property. Convolution, the DFT and inverse DFT can be used to multiply two polynomials, so we can get the quotient of the product polynomial quickly if we can compute the DFT and its inverse quickly. A naught A n minus 1 B naught B minus 1 paired with n zeros, paired with n zeros, it becomes A naught to A n minus 1 0 0 0 B naught to B naught DFT. Then we get Y naught to Y 2n minus 1 is naught is 2 minus 1. Component multiply, then Y naught is not Y1 is 1. Inverse DFT, C C1, C2 convolution. Fast Fourier Transform, the FFT is an efficient algorithm for computing the DFT. FFT is based on a divide and conquer paradigm. If n is even, we can divide a polynomial P of x is equal to A naught A1 x A2 x squared n minus 1 as P even is equal to A naught A2 A4 an minus 2 P out is equal to A1 A3 F8 so on. So P of x is equal to P even into x squared plus x into P out into x squared. After the FFT algorithm is shown here, the running time is of the order of n log n. Inverse of FFT is similar. What is spectrum? Defining of spectrum. Spectrum modulation refers to any modulation scheme that produces a spectrum for transmitted signal much wider than the bandwidth of the information being transmitted independently from the information bearing signal. Reference Introduction Spectrum Communication by Peterson, Zimmer, and Borrow, 27, 1995. A simplified block diagram of a narrowband communication system. Amplitude versus frequency show narrowband waveform. Message or carrier oscillation transmitter. Then it goes to the demodulator where the receiver and message is called back. Simplified block diagram direct spectrum communication system. Carrier oscillator, mixture, PN pseudo-random number generator, then transmit, narrowband waveform, spectrum waveform, and receive mixture, PN generator, demodulator, and the message is received. Spectrum underlies a display of a direct sequence spectrum waveform or from spectrum C magazine is shown here. Amplitude, there is a main lobe and there are side lobes of the same frequency. Frequency hopping spectrum. Spectrum is a display of a Fourier hopping spectrum waveform as shown in figure. Around is just overlay immunity for interference, aka anti-jamming special spectral efficiency relates to capacitive users cause multiple access capability, CDMA, multipath rejection, signal capture process range in GPS. This is an issue with the amateur and other communication community, privacy and inherent property, usually referred to as LPI, low probability of intercept, or SLPR, low probability recognition, raising the noise floor, corruption of incumbent users, particularly weak signals and repeaters. HTS spectrum started in 1920 with the advent of radar, enhanced resolution, World War II military use to combat jamming, 1959 John Costa's K2EN, Poisson, Shannon, and the radio amateur, 1970 global questioning system, 1985 Part 15 devices for interference resistance and chat communication properties. 130 companies have developed more than 200 systems and products, and more than 3 million devices are now in use by consumers and businesses. Spectrum, analog or digital data, analog signal, spread data over wide bandwidth, making jam and interception order. Frequency hopping, signal broadcast or seemingly random series of frequency, direct sequence. Each bit is represented by multiple bits in transmitted signal, chipping mode. Input fed into channel encoder produces narrow bandwidth analog signal around central frequency. Signal modulated using the sequence of DC spreading code sequence, typically generated by pseudo-random number generator. Increases bandwidth significantly. Space spectrum receiver use the same sequence to be modeled clearly modeled. Signal fed into channel decoder. A general model of space spectrum system. So input data, channel encoder, modulator, pseudo-random generator, spreading code, channel, demodulator, spreading code, pseudo-noise generator, channel decoder, and output data. Gains. Immunity from various noise and multipath distortion, including jamming, can hide encrypt signals. Only receiver known spreading can data signals. Several users can share the same higher bandwidth interference. Another form, code division multiplexing, code division multiple access. Pseudo-random number generated by an algorithm using initial seed. Deterministic algorithm, not actually random. Algorithm could resist false reasonable test of randomness. Need to know algorithm and seed to predict sequence. Frequency appearing space spectrum. Signal broadcast over seemingly random series of frequencies. The receiver opts between frequencies in single transmission. Eavesdroppers hear unintelligible blips. The jamming on one frequency affects only a few bits. Basic operation, typically 2 carrier frequencies forming 2 channels. Channel spacing corresponds with bandwidth of input. Each channel used for a fixed interval, 3 millisecond in IEEE 802.11. Some number of bits transmitted using some encoding scheme may be a fraction of bits. Sequence dictated by spreading code. The energy versus frequency for channel assignment and channel use are shown in figure. Channel use uses time and frequency. Frequency of space frequency system, transmitter, binary data, modulator, FFT or BPSK, output of the modulator is fed to the pseudo-random bit source and channel table and frequency synthesizer, CFT, FS spreader, then bandpass filter about some frequency, space spectrum signal SFT is obtained. The receiver spectral signal SFT is given, and then pseudo-random noise bit source, channel table, because they give CFT, they are mixed. The spreader STFT is formed, bandpass filter about different frequency, demodulator FSK, BPSK, and binary data is obtained. Slow and fast FHSS, frequency shift every 30 second, duration of signal element is 10 seconds. Slow FHSS as TC greater than equal to TS, fast FHSS as TC less than TS. Generally, fast FHSS gives improved performance in noise or jamming. Slow frequency of space spectrum using MFSK, M is equal to 4, K is equal to 2 is shown in figure. PN sequence and the binary data. Y-axis is the frequency and the x-axis is the time. For the different input sequences given in the figure, for frequency of spectrum using MFSK. FHSS performance consideration. Typically, large number of frequencies use improved resistance to jamming. Direct signal spectrum, DSSS, each bit represented by multiple bits using spreading codes. Spreading codes spread signal across wider frequency band in proportion to number of bits used. 10 bits spreading code spread signal across 10 times bandwidth of 1 bit code. One method, combine input with spreading code with using XOR. Input bit 1 inverts is a spreading code bit. Input 0 bit does not alter spreading code bit. Data rate equal to original spreading code. Performance similar to FHSS. Direct sequence space spectrum example shown. The transmitter side and data input locally generated PN bit stream and transmitter signal are shown, and receiver receives signal locally generated PN bit stream identical, and the data output are shown. Data sequence spectrum transmitter, binary data, modulator, BPSK, pseudo-random bit source, they are mixed. The spreader is done. Spectral signal is obtained. Spectral signal given, and then the spreader is used with pseudo-random noise bit source, and then demodulator BPSK used to get the binary data. Data signal spectrum using BPSK example. DT data, the SDT, CD, and FT waveforms are shown here. Approximate spectrum of DSS signal energy is shown, and spectrum of pseudo-anonymous signal and spectrum of combined signal all are shown in this figure. Code using multiple access, multiplexing technique used with spectrum. Start with data signal rate D, call bit data rate, break each bit into chips according to fixed pattern specific to each user's code. New channel as chip data rate KD chips per second. Example K is equal to 3 users ABC communicating with base receiver or code for A, B, and C are shown here. Message is encoded by the different users with a different code as shown in figure. CDMA explanation, consider A communicating with base known as code, assume communication already synchronized. A wants to send A1 send chip pattern yes code. A wants to send 0 send chip pattern to get complement of S code. Decoder ignores other sources when using A code to decode orthogonal codes. CDMA for DSS, the end users each using different orthogonal P and sequence, modulate each user data stream using BPSK, multiply by spreading code of users. So D1, D2, D3 are given added, and S1 is sent here and then transmitted along with the noise and received. C1T is fixed, and then cost to P FCT get the D1T. 7-channel CDMA encoding and decoding is shown here. 0 to 7 channels, channel core, composite signal is shown, and then it is added together to get 9. Thank you.